Okay, so let's keep talking about comparison of methods. In 2016, Anders Eklund and colleagues published perhaps one of the single most influential papers in this context. And they did the following really cool experiment. They downloaded and they took data from several repositories, and they took resting state data sets. In fact, there's one from Beijing, 198 subjects, one from Cambridge, also 198 subjects, and then a third data set of over 100 subjects. And these were all resting state data. So in the sense, these are all null data sets. There's no task. And so they thought, let's pretend that there is a task and do a full analysis, and then see if we get any positive result. If we do, that will inform us on the number of false activations, the number of false positives. So they did the following. For each subject from each of these data sets, they pretended to have 4 different possible tasks. There were 2 block tasks, so they modeled, they pretended that tasks were happening. Once they pretended that it was a block design, 10 seconds on, 10 seconds off, and then they did the whole analysis and they looked at how many positives they would get, even though, of course, there is no task. This is an H0, this is a null data set, right? It's a resting state data set. Then they pretended to have B2, some an on-off block design with 30 seconds on, 30 seconds off. And then they simulated 2 different event-related design, one with 2 seconds activation and 2 seconds rest, and one with 1 to 4 seconds activation and 3 to 6 seconds rest, but randomized instead of jittery. And so they used all these different designs, pretending. They said, well, but if our task was like this, even though the participant was obviously not doing any tasks since it was a resting state, how many times would we get a positive result? And then they varied a number of important factors. They looked at different levels of smoothing, 4, 6, 8, 10 millimeters, full width, half max. They did a 1 sample t-test, a 2 sample t-test for group differences. They sometimes used 20 groups of 20 subjects versus 40 subjects. And then they did both voxel and cluster analysis. And when they did cluster analysis, they would either use a threshold of 2.3, which is 0.01, or a threshold of 0.001, which is a Z of 3.1. And then again, for each of these, for all the different permutations of this analysis, they report how many times when they do a group analysis do we get a positive result, knowing full well that we should get none. So this is just a really interesting empirical way of assessing all of these different approaches for how well they control for alpha, for the false positives. Now, the most interesting aspect of this is that they performed a number of different analyses. At the group level, they either did a random effect, so this means SPM using only the between subjects analysis, FSL also using an OLS, so again, only using the between subject variance, not without using the within subject variance, and AFNI using 3D t-test, which also ignores the within subjects variance. Then a second group of analysis were done using a mixed effects approach, so combining both within and between subjects variance as the yardstick at the group level, and FSL does that with Flame 1 or with Flame 2. And then using AFNI 3D MIMA. And then finally, the last approach was a non-parametric or a permutation approach. And they used a tool called Broccoli, which is exactly the same as FSL randomized, although it doesn't have some of the perks of FSL randomized. However, Broccoli runs on the GPU, which means it runs infinitely faster than FSL randomized. In fact, somewhere in this paper, they comment, had we used FSL randomized to do the same thing, it would have taken us, I don't know, 10 years, some crazy number. So now the real question is, under knowing full well that we have a null data set, how many false positives do we get under each of all of the permutations of these analyses. So first, let me introduce these graphs. What this is showing is the family-wise error rate for each of the different analyses, which you see down here. Now, the important thing to know is that you would expect this is your 5% error rate. This is what you expect analysis to have just about 5%. And so any analysis that is somewhere inside this bar, it means that it's within the 95% confidence interval for 5% family-wise error rate. So that would mean that your analysis is valid. If your analysis is below that 95% confidence interval, then it's valid, but it's conservative. On the other hand, if it's anywhere above that, if you have more than the 95% confidence interval around the 5%, then it means you're not controlling properly for your type 1 error, and you have an inflated alpha compared to the nominal 0.05. So how do these different approaches do? And here we use the 6 millimeters smoothing. It's a one sample t-test done on the Beijing dataset. And the cluster determining threshold here is 0.01, which means Z 2.3. If you were to use the SPM OLS approach, this is what you actually get. And the different bars represent the different designs. So this was the block with 10 seconds on and off. This was the block with 30 seconds on off. And these two are the event-related designs. This is the sort of slowish event-related design. And this is the jittered event-related design. So regardless of which one you're using, at best, you have a 15% empirical family error rate, family-wise error rate, as opposed to the expected 5%. At worst, we're somewhere close to 50. Definitely not valid. If you do any of the other OLS analysis, you get the exact same result. So if you do a random effects analysis, you are way above your nominal error rate, meaning you get a lot of false positives, despite the fact that this should all be null data. Then, if you instead do the same with Flame, FSL Flame, you actually get a pretty good result. You get a valid analysis for event-related designs. You seem to get maybe 12, 13% alpha if you use the block designs. But if you use 3D MIMA, which is the AFNI tool, you actually still get very high empirical alpha, and that has to do with just the specific way in which 3D MIMA estimates the average smoothness from the first level analysis. It just does it in a way that essentially ends up not helping quite as much as, for example, the the within subject error does in the FSL analysis. It's just the way in which they go by estimating it is probably the problem. What is interesting, however, is that if you do the permutation, you are pretty much within nominal alpha, within range of the nominal alpha. So as you notice, the main issue here is that all the parametric analysis, for the most part, I guess with the exception of Flame 1, of FSL mixed effects, really give you highly inflated alpha. On the other hand, the one that seems to control well for it is the non-parametric analysis, the permutation analysis. Now, if you do this at a cluster level of 3.1, so exactly the same thing, same data set, same one sample t-test, 6 millimeters smoothing, and a 0.001 or 3.1 Z threshold, then the results are generally much better, although you're still getting, for most analysis, more than the nominal alpha. Notice that Flame becomes very conservative, and this is just, I I don't know the exact reason for it, but the null distribution, the null t-stat distribution in FSL Flame happens to be leptokurtic. I don't know the origin of it, but that's just what it is. And so as a consequence, it becomes very conservative very quickly. On the other hand, if you do permutation analysis, you're still perfectly within the 95% confidence interval, even at 3.1. Finally, if you do a voxel level inference with 0.05, you get, for the most part, either conservative or valid analysis. But of course, this would be the case of Bonferroni, right? The risk here is to get a lot of false negatives. And you can show this, in the Cambridge, just to show how this sort of extends to multiple data sets. In the Cambridge data set, the results are pretty much the same. So very clearly, if you do a random effects analysis, if you do random effects analysis with a low threshold, you're almost always guaranteed to be well above, and I mean well above, 10 to 20 to 30 to 50% above your nominal alpha. On the other hand, if you use a cluster of 3.1, the worst that happens to you is that you get very conservative results, which could be a big problem, and we're going to discuss this, in fact, later on. On the other hand, if you do a voxel analysis, you're typically very, very conservative, again, with the exception of the permutation testing, which whatever analysis you use, thresholding you use, tends to be pretty good. Now, in this paper, they also looked at one fairly often used strategy, which they refer to as the ad hoc clustering, probably because it just has it's just been used for a long time, and that's the basis why it's been used. And it does happen often that people will do a cluster correction at 0.001 uncorrected, and then will impose that I am doing this sort of fairly lenient thresholding, since it's 0.01 uncorrected, but I will require at least, let's say, 10 contiguous voxels. In other words, I'll use 0.001 to get my peaks, but then I need a voxel, a cluster of at least these many voxels to be considered a chunk. Now, the real problem with this approach is that not knowing how smooth your data are, saying that I need at least 10 voxels means nothing. It doesn't, 10 voxels, I don't know, if your data are very, very smooth or very, very spiky, right? It might be perfectly reasonable to get a lot of at least 10 contiguous voxels active according to how smooth or spiky your data are. So just saying 10 voxels is not a theory-based, it's a completely arbitrary way of doing it. There are ways of achieving something similar to this with AFNI using Monte Carlo simulations. But this particular way that is used, that I'm referring to here, doesn't sort of come from a theory approach, but more from an empirical and kind of practice-based, I guess, approach. And so what they show is that, for example, if you do this with SPM, you end up having possibly 60 to 85% false family-wise error rate. And in fact, the truth is that you end up getting really inflated estimates, family-wise error rates across the board, perhaps with the exception of Flame 1. And I'm guessing this is just because of how the variance is calculated, that random effects, that mixed effects yardstick that FSL uses. So what's the problem here? Well, multiple ones. For one, as we said, the betas are not normally distributed. We've seen this in the Thirion and colleagues paper a few slides back. Second, it's just that the hypothesis, there's some specific hypothesis of the Gaussian random field theory for cluster-wise inference that just don't hold. And it's two in particular that apply to cluster-wise RFT thresholding. First, they assume stationary spatial smoothness. What I mean is that over space, the smoothness of the data is expected to be stationary, to be the same, and not to be different in different parts of the brain. Turns out, as you can see from this image here, the whiter each voxel, the color of the voxel indicates how smooth in that region the data are. So what you would want is, you would want all this to have the same color. Instead, as you can see, there's a lot of variance over space in terms of the smoothness. And it makes sense because cortex will definitely have a different smoothness than the white matter. But on top of that, as you can see, different aspects of cortex, for example, this is the precuneus area, right here, you can see that it has very different smoothness, that and the medial prefrontal, than many other parts of the brain. So this assumption is definitely violated. On top of it, it turns out that if you look at what are the areas that tend to have false activations, they fall exactly in the areas of different smoothness, right? Where it's more non-stationary, where the smoothness is more non-stationary, you get more false activations. Oops. And see, if you flip, you can notice that where here there's a lot of non-stationarity, so they're the white voxels, that's where you get, as you see here, more false activation. So definitely the first assumption is not met. The second assumption, specific to cluster analysis, is that the spatial autocorrelation function, so the correlation over space, has to have a specific, is assumed to have a specific shape, which happens to be a squared exponential over space. So this is the correlation over nearby voxels, or rather the correlation of a voxel with all the other voxels, depending on how close they are. It's supposed to have this particular shape. The correlation with nearby voxels is very high, and then as you go further and further away, the expected correlation should drop off quite a bit, right? So the dashed line is the expected correlation over space. So if I have one voxel and I pick a voxel that is only, let's say, 2 millimeters away, I expect the correlation to be 0.9. If I pick a voxel that is 3 millimeters, well, I guess 4 millimeters away, then I'd expect the correlation, sorry, it's the dashed one, to be, maybe 0.75. And then as two voxels get further and further away, you expect the correlation to diminish. And that's why you see the dashed line here falls off. And by the time you're at, 14 or more millimeters, you should expect very little correlation in those voxels. Turns out, however, if you look at the actual empirical autocorrelation function over space, you actually get much larger correlation over space. So even far away voxels tend to have much larger correlations than you'd expect. And so we're violating this second assumption. And it turns out that it doesn't even matter what software you use. This pattern is true of every software. So if you use SPM, you can see that the full line, right down here, you have way more correlation among distant voxels than you'd expect to have, than you're assumed to have. The same is true with AFNI OLS. The same is true with FSL Flame, with FSL OLS, and with AFNI MIMA. So this problem is true across the board. Notice, however, that for short distances, so for voxels that are nearby, the approximation holds pretty well. So, whereas it's for the longer distances that the approximation breaks down. So this might explain why, when you have very high threshold and you only get voxels in small clusters, if you only get small clusters, this might explain why you don't get a lot of false positives at high thresholds. Whereas at low thresholds, where the right part, the red part of the graph comes into play, you get clusters that extend more than 3 millimeters. Or much more, then there, yes, you do get a lot of false positives. So the way in which this particular assumption is violated might explain why at high threshold you get perfectly valid results, but at low thresholds instead you get a massive inflation of your family-wise error rates.